this morning and also for bearing with us on our modified processes. I think it's very important that we get this information in people's minds. And I just want to thank you very much for the quality of your participation and the efforts you're putting into this. We need you to succeed. Thank you.
Thank you. You're welcome.
Yep. Thanks for the opportunity and the dialogue. It's very much appreciated.
Take care.
Right. So here's the plan. The plan actually hasn't changed from the agenda we sent you, but I want to remind you, we're going to break for lunch at 1:30. Karthik is going to be with us with a presentation on the tank leak assessment process. And then that will lead into a discussion of the draft advice that is being developed. As Steve has said, because we want to make sure that all of the seats on the board can participate fully, we're not taking any consensus action at this meeting, but we do want you to be able to look at what's on the paper and ask any questions that you have or make any comments that need to be made. And we will wrap up the day with some board business that we're moving from what would have been day 2. So that's the plan, and we hope to see you back at 1:30. Thank you.
Thank you all. So Ruth,
Yeah.
before we start the discussion, I'd like to state our meeting context one more time.
Cool.
Okay.
So we have a DFO, we have a chair. Psychology and we Roberto will join us with EPA as soon as he is done with the EPA administrator. So we've got those bases covered. Steve, would you like to do the intros before we jump in?
Sure, you bet. Thank you. I would just like to restate the context of the meeting so that it's clear to everybody. This is an informational meeting, not a decision-making meeting. And that is because the board requested to DOE that we not vote, because there are a number of members, very important members, who would not be able to participate in that vote. So we asked permission to make this an informational meeting. There was some media interest in the potential that DOE had blocked us from voting, and that is not the case. That was requested by the board. Our vice chair and myself, Shelley Simone, collaborated and asked DOE's permission to proceed with the meeting without voting. And that allows us to get up to date on important issues, including the one coming up related to tank leaks, but that we will postpone any vote determination until the board has been fully approved and we can have the right kind of participation from critical members. So I just wanted to restate that as a starting point for the conversation. And I appreciate everybody's forbearance in understanding the fact that this meeting is important to us, but it's not going to be a business meeting.
We have a question from Jerry Paulette. Jerry?
Okay.
Thank you. I want to clarify from our prior discussion that this does not mean that we cannot ask each and every member of the board, including those people who are awaiting reappointment, what their view is on the draft advice and have that feedback from every single party on the board, whether or not USDOE has incompetently withheld reappointment. And that's being kind, I think. But it's most important that we have a discussion and see where we are as a board on really important advice. Because contrary to comments earlier this morning, if this board is not responsible and expected on behalf of the public and our constituencies, including from my organization, 10,000 members across this region, to be giving advice when there is something as important as an emergency or a tank leak, then we have a real disconnect. So I'm hopeful that we'd be able to have essentially what we've called a sounding board. And is that the case that we'll be able to do that?
I think it is important that we hear from members who have something to offer, and as time permits, we'll definitely plan on doing that, because it's important as we go forward that the draft advice that's being considered is fully discussed by our membership. And so we definitely do want to know what folks think. So we'll proceed that way. We're not holding up the advice from proceeding. We just want to do it in the context of the right membership being available to participate formally in the process.
Stan Branch, your hand is up.
Just want to state that it's not a competency issue that we're working with. We have a process in place for approving packages, and that's at headquarters. So we're waiting for that response back from headquarters on all of the packages. Thank you.
All right. So Karthik, are you with us?
I'm here, if you can hear me.
I can hear you.
All right.
I've got a presentation, and you boss me around, and
What's up?
and we'll do it.
Well, it'll be the first time somebody listened to me bossing somebody around. So,
Yes, you have to tell me where to go.
all right, okay, there you go. So welcome, thank you all for joining us. I have, so my name is Karthik Subramaniam, the Chief Engineer for WRPS, the current tank farm operating contractor. I believe I know most of you, or you've seen me give presentations on tank integrity over the last several years, whether it be in single shell tank integrity or double shell tank integrity. And this is an update on tank B109. There's a lot of interest in our leak assessment process and the way we use our data and our inputs and our calculations. So I think it's our opportunity here to go through all of that data so we can go through the details of the report and then answer any questions that y'all may have in relation to how we came to the conclusions that we did. So with that, slide 2, there we go. So on slide 2, I'll go through the background on single shell tank B109. There's a lot of details there. Obviously, B109 is in the B complex, is one of our older tank farms, single shell tank farms with multiple types of tanks that are in the B complex, and particularly in B tank farm. We'll review our tank monitoring and integrity program, as I do every time, to get us on the same page for the functions and the requirements that are outlined in our 9937 document, where there's a lot of input and collaboration with the Department of Ecology and others. And then technical interpretation of the waste level chart and the leak assessment report. And that's the interstitial liquid level report. And that's the interstitial liquid level waste level chart. We'll go through the details of how we monitor from our engineering standpoint, and the team that is pays attention to that on a daily and continuous basis, not only for B109, but for all of the tanks that we have, LOWs and NRAFs and so forth. Obviously a very important program for us. And then review in detail how we calculated the total leak volume of the 3,100 gallons when the report was released. And that is in the context of our visual observations as well as our empirical observations with the the liquid observation wells. So if I do have acronyms in there, please stop me or ask a question. I'll try to explain the acronyms, and we'll go through those details. We do have mitigation in place already through our groundwater measures in B complex. We know B complex has had a pretty significant amount of subsurface contamination already. And these mitigation measures were in place. And then there's other things and some options and the associated challenges that are under consideration. And there's a series of those, and we'll go through some of those details, whether they be physical challenges, operational challenges, or straight chemistry challenges. And then again, ask questions. Ruth, would you like to keep the questions till the end, or let me answer questions along the way?
So what we usually do is you'll share your information. We'll check in with Ecology. I believe Nina Menard is with us from Ecology, and then we'll go to questions.
Okay, thanks, Ruth. So a little different than we've done it in the past because we build on the information, but certainly virtually makes it a little more organized then. And then we'll summarize and then answer the questions as we go. Okay, thanks, Ruth. Next slide, please. So tank B109 background, it is a 530,000 gallon underground single shell tank. So this is one thing I think that is really important. So in contrast to some of our other tanks, this is a type 2 tank. It is 75 feet in diameter, but it's 10 feet shorter than some of the other tanks. And so being that it's about half the size of a 1 million gallon tank. So something for us to recognize. Not every tank is 1 million gallons out at Hanford. Some are 530,000 in this particular type 2 tank, made of a 1/4 inch mild carbon steel with some knuckle plates on the bottom. And it's a dish bottom with a 4-foot radius knuckle that's in there in B tank farm. So a little different than what I've talked about before in the 1 million gallon double shell tanks. 1946 to 76, contaminated liquids. Obviously, we understand that. Lots of work, bismuth phosphate waste, so forth, so on. Over years, some evaporator waste over 30 years. After that, 1985, we did go through an interim stabilization campaign for all of these single shell tanks, and what the pumpable liquids were removed as part of this. And I think everybody is aware of this history there. And pumpable liquids, that's an important parameter. Every one of these tanks is going to have some residual liquids, and those residual liquids are not pumpable, so they're not removable with our current technologies, but they will be removed over time as we get into our waste processing mission. Today, the tank does have a solid salt cake and sludge and residual liquids in it, and the numbers, let me make sure I get these exactly right. And so 51,000 gallons and then 13,000 gallons of what's called drainable interstitial liquid. So I do want to go through some definitions here. So being that it is sludge on the bottom and then salt cake and then some potential supernatant on top. Interstitial liquid level is the height of the residual liquid that occupies the spaces in the solid waste heel of one of these interim stabilized SSTs. So that invokes the idea of porosity or some airspace even within the solid salt cake and solid sludge. There is porosity in these liquids. Drainable interstitial liquid is really what is the volume of interstitial liquid that's available to drain if there was a leak within the tank itself. And that is a function of whatever the waste volume is, and by waste volume and the characteristics of what is the sludge content, the salt cake content, the porosity content, which is really done, the porosity is estimated via some analysis that's been done over years on the types of waste in these tanks, and then the capillary height for how it sticks to these areas. These were updated and released several years ago, and then they're obviously in our monthly waste tank summary report. All of this information is published on a monthly basis. So this leak is detected by the waste monitoring, or if we were to have a leak detected by waste monitoring and a tank integrity program. Our tank integrity program, you've seen my previous briefings, continues to evolve, continues to get better, continues to use new technologies, whether it be in the arena of chemistry or in the arena of visual inspection of what's on the waste surfaces, as well as the structural. I'm sorry, I like to wave my hands when I'm explaining things, or on the dome surface, on the interior of the surface. So we're certainly very interested in the structural capacity of the tanks as well. So in this case, as you all well know, we do have a very formal leak assessment process. B109 was declared leaking in April 2021, and an estimated total at that time was of 3,100 gallons. And we'll go through what that process is to estimate that 3,100 gallons. The leak is far underground, we know that. Certainly it's not a surface spill, so the immediate risk to workers and the public very different than what we might see if it's a surface spill. We do know that the tanks are well underground for shielding purposes as well as other things. And so while it poses no immediate safety risk, we take these things very seriously and go through not only the leak assessment process, but ensure that our mitigation measures that are in place still have that margin against any of these spills that may impact total subsurface work. And leak, in terms of the environment in the B complex, there have been extensive contamination for fast operations, and those past operations led us to a groundwater remediation program, and the past leaks led us to that. And this certainly falls within the boundaries of the margins that are established for groundwater contamination. So, and the impact in terms of what is the reduced margin is very small compared to those things, and what is already in place in terms of volumetric capacity to be able to remove contaminants from that. And that is the groundwater treatment mitigation that's already in place, and that's the pumping system. And we'll go through all of that. So a couple of important things: B109 is physically different than a lot of the tanks that we talk about. It is about half the size of the 1 million gallon tanks. It does have sludge and salt cake within the tanks, and it is, although it is not, we haven't confirmed rainwater intrusion. We do claim that it might be rainwater intrusion in that site. It's in one of the tables, table 4.5 of the monthly tank waste summary report. So all of this being said, we do have an integrity program that's guided by our tank integrity expert panel. And we've been continuously evolving that over the last 10, 15, 20, 30 years now, and we continue to get better. Okay, next slide, please. So this is our tank monitoring and integrity program. We have now implemented RPP, called 9937. It is the SST leak detection and monitoring functions requirements document. We are now on Rev 4 of that. Rev 4 was signed off earlier in this year, and now we'll be implementing the requirements of Rev 4. So we take periodic waste level readings. It really depends on the tank itself. Some are quarterly, some are monthly. We use two types of real waste level gauges. One is an NRAF if there's liquid material that's on top, but primarily liquid observation wells that measure the levels of liquid in the salt cake and sludge. And so I do want to be clear here, the way an LOW works is it's a fiberglass tube. that goes into the waste itself. Then you measure through some scattering measurements what is the level of liquid in there. As we know, the waste in these tanks does move. There's lots of characteristics of these wastes. And so as we go through the process of liquid observation wells, that's the type of information that we use to calculate what our interstitial liquid levels are. But those liquid observation wells and the interstitial liquid levels also, we know from experience in these tanks and a lot of experience within operations and engineering groups, there are multiple things that impact what the ILL does. And that's the process that I'll go through on the chart itself. Periodic tank interior inspections using remote cameras. We not only do this in the SSTs, but the DSTs. As you might imagine, it's not really easy. Cameras in general, some of the challenges associated with this, certainly lighting in the tanks. We've gotten better and better at lighting in the tanks, new technologies and cameras that can last longer within the radiation environments that are in the tanks, as well as if there's any ability to make sure that the camera lens doesn't fog up. So lots of challenges with getting into these tanks through some small risers. And you have a very basic diagram there of the tank itself. It is a single shell tank, carbon steel liner that is intimately attached with the concrete vault, and then a liquid level gauge notionally, an LOW in most of the tanks, and then the ground level. One of the things that we are most interested in is the structural capacity of the tanks. So we have a very detailed dome load program, a highly conservative dome load program that leads to an analysis of record. And in that, we account for all of the mass and weight on top of a tank, and then we track anything that is put on top of a tank to ensure that we don't challenge what the dome structural capacity is of the tank itself. This is done through a structural analysis program, as well as within engineering itself. We have procedural controls to track and monitor everything that's put on top of a tank. Along with that, we have a dome deflection program. So if there's any notion that the dome is deflecting at all, then we can go back and turn around and see whether there's, if the dome is moving, then that gives us an indication of any structural issues that we may have with the dome. So one thing to remind us, in this tank itself, while the walls have a carbon steel liner, the dome is just concrete. And so our tank monitoring integrity program for single shell tanks is really, it's really very complete. Visual inspections, we have liquid level types of measurements. We take those empirical measurements, make the calculations that we all see that are published in the tank waste summary report. And then internally also, as we're following all of this, we do inspect for dome integrity. We're interested in the condition of the concrete as well. And then all of this information is to identify potential intrusions, potential leaks, and then we want to monitor any liquid level changes before and after any in-tank activities. However, very few in-tank activities do take place in these old farms. Okay, next slide, please. So this is the report that was. Can you see my pointer? Oh no, you're sharing. Okay.
Yeah.
Sorry. All right.
Sorry.
Let's see if there's a way to do that. So in this is the ILL interstitial liquid level report that is actually presented in the report itself. As you see here, I'll just go in through the first, or I don't have a pointer, but let's see if there's a way to do that. So if you could start all the way.
That's my pointer. So if
yeah.
I don't know, let's see if you can boss me around.
I'm not sure I can. That's okay. I'll try to explain it in the context of the Y and X axis. Okay, so on the X axis here, you'll see that it's actually 24 years presented of the interstitial liquid level. And then on the Y axis, it's the level above the tank centerline bottom. And that goes from about 40 inches to about 44 inches. So that's the graph. For us to remember, it's about 2,750 gallons per inch. Okay, and so you see from about 2004 over to 2013, 2016, about a steady increase average, but as with all empirical measurements, oh, sorry, Ruth, there you go. As with all empirical measurements in an LOW, We see this in lots of tanks. It's not a perfect line. Our LOW, as I said, the waste does move in these tanks for a whole variety of reasons. Salt cake does tend to collapse over time, and then that would have waste that goes out or waste subsidence. Salt is obviously not it'll fall in on the weight of itself. Gas bubbles, there's retained gas movement within the porosity of these tanks, particularly if you have a sludge tank. And so that tends to move waste around as well as influence these. There could be water intrusion in this tank, although we've never confirmed water intrusion in tank B109. It's on this list because of the steady increase. And you'll see this choppy work on ILLs, but we obviously on a quarterly basis, we track this to and ensure that we don't really have changes that are indicative of any of changes other than waste movement, other than retained gas movement, those kind of things. So as the waste collapses around the LOW, it could push the liquid away from the LOW. So lots of things go into how the waste, I don't want to say performs, but how the waste moves within the tank within this 3-inch fiberglass tube and how that impacts our ILL. So what you see there, I've actually circled, so don't make it hard. So there's just the first circle around the 2016 timeframe. There is a 1/2-inch decrease, about a 1/2-inch decrease, which indicates we immediately got interested. Why is there a 1/2-inch decrease in this? Because that's a pretty significant change. But you'll see some other decreases along the way that are not quite a 1/2-inch, but something less than a 1/2-inch. One of the things that we really look for, and that is indicative of waste movement, is if the 1/2-inch decrease is immediately followed by a recovery of that. So what that means is the waste has resettled back into the condition that it is. And if there was a retained gas movement, then that retained gas is now resettled the waste into those, and the liquid is resettled into those things. Now, as we track that, as we move on to where we were here, so now in 2018, between December of 2018 and about March of 2019, in that quarter, now we see a 1.2-inch decrease. Now, what this means is without the recovery, what does it stabilize at that point? So we increase the monitoring frequency from quarterly to monthly. So our trending could really move and have more data points along the way. So again, we're looking for waste collapsing. We're looking for retained gas movement. We're looking for those kind of things that would be indicative of anything that happens in a tank including up to and including tank leaking. So we increase the monitoring. Now, then we try to see if the level has stabilized, and if the level, that's number 4, if the level stabilizes over a period of time, then that again indicates, most likely in this case with that significant decrease, that indicates when the level stabilizes, that indicates a collapse of the waste and a condition in which now we have an idea that the collapse of the waste has pushed the liquid out of the LOW. So we see that decrease. Now, let's see, let me go to number 5. If that stabilization of that particular waste doesn't continue to be stable, we see another decrease, and you can see another decrease in that point right there, number 5. Yes, then a formal leak assessment begins in July 2020, and we went back to a monitoring frequency, changed back to monthly. So the reason that formal leak assessment here begins in July is because there is a very detailed process, proceduralized process that we follow with the elicitation process as we calculate these. But there's nothing that happens along the way that says informal leak assessment. So continuously we're monitoring any changes, knowing that there's 5 or 6 independent variables that could have ILL changes. So the formal leak assessment process, there's actually a process by which we put a team together, take all of the data that we have available to us, and then identify what the probabilities are of this tank being a leak. And as you might imagine, any changes along the way are monitored, whether it be on a quarterly basis or a monthly basis, and all of those options are always on the table. So we do take this process of monitoring ILLs very seriously, and although not entering a formal leak assessment process until we have good knowledge of change, we have a leak, my words, an engineering leak assessment process all along with every data point that we see along an ILL. And then let's see, where number 6, we had actually finished this formal leak assessment process with all the data that went in. We wanted to ensure we hadn't done dry well logging in a very long time in this area. And so we wanted to go do dry well logging right outside that tank in March. And that was the last bit of data that confirmed that the probability of that this tank was leaking was high. And that leak assessment was completed. We inserted the data from the dry well logging, and then the leak was declared in April 2021. Having said all that, I think a couple of points on this graph. One, our empirical analysis of our LOW scans sees a lot of this choppy ILL scans as we go. Not surprising, the waste does move in our tanks. The waste does have, particularly in a tank that contains this amount of sludge, retained gas movement. The salt does collapse over time, and all of these things lead to this analysis. And then secondly, as we see decreases in this, we enter formal leak assessment processes if those changes don't stabilize over time. But however, our leak assessment process is continuous along the way, and all of the ILLs, like I said, are published along the way as we do this. So, so at the end of the day, our team of experts did complete the leak assessment process and declared it in April 2021, and I believe that is now published also in the monthly tank waste summary report. Let's see, I think I went over everything on this slide. Okay, and this is data as of April of 2021. And so, and obviously we continue to track the ILLs and calculate this. Okay. So how do we estimate the total leak volume? I'm going to try to do this without a whiteboard, which I usually do a better job of, but it's 2,750 gallons per inch, and it's a 75 foot diameter tank in the cylindrical region of the tank. The composition is about 41% sludge and 59% salt cake, excluding any supernatant that's estimated in there. Now, waste on the surface is salt, and you can see the visual images here. In a video it looks a lot better, but as we capture screen, sometimes it doesn't go real well. We pour over these videos slowly, hours and hours of video. The salt cake waste porosity is estimated at 24% based on some of the knowledge of the types of waste we have in here, some reference documentation. So the liquid present in the waste is the combination of the free liquid on the top plus the interstitial liquid. So the free liquid on the top of the volume is equal to the 2,750 gallons times the surface liquid fraction. And what you see as we go through the video is that we estimate what that liquid fraction looks like. So 2,750 in a 1 inch period. If the entire 1 inch is not covered up in liquid, whatever the fraction of the surface is covered up in liquid. Okay. And then the surface solid fraction is 1 minus the liquid fraction, and that's the solid fraction that's not part of the liquid calculus there. So then the interstitial liquid volume is equal to the 2,750 gallons times the solid surface fraction times the porosity for the salt cake as well as the sludge. So some of the details of the liquid here. On February of 2014, as you see there, somewhere around 46% liquid surface from the inspection. In 9/22 in September of 20, about 9%, and then on February 21, it's less than 5% of the liquid surface. And all of this is calculated as we go through the video and estimated. That turns into an interstitial liquid level on those 3 times of 43, around 43 inches down to 40 inches and then 40.21, as you saw on the previous graph there in 2021. Now, that gives us the empirical information based on the interstitial liquid level. But one of the things we're also interested in is having some visual things to make sure that we're not missing any other visual cues that may give us a different piece of information. And you don't see this on here, but there's a salt well screen that's also was installed, abandoned in place in this tank itself. So we also have a mark on the salt well screen that we can then follow what that liquid looks like on the salt well screen. And then we can calculate, based on the liquid level on the salt well screen and then the liquid level as it moves along the salt well screen, that gives us a reference point on the screen. So we want to use all of the types of information that we have. So using the waste level calculations, as well as from the ILL information, as well as the salt well screen information with visual observations, all those calculations are used to, so that you use the interstitial liquid level to estimate the volume decrease, and then you use the salt well screen to estimate the volume decrease simply on visual observations of that particular area. And then we estimate it conservatively, use the average of both of those. And that was a total volume lost between February of 2014 and February of 2021, gives you 3,100 gallons lost. So a lot of calculations that go into this on the physical observations, the empirical observations, the visual observations, and all of this video that takes place, in addition to the details of the types of waste and the porosity and the capillary height. So we try to get the most representative gallons of liquid lost, potential liquid lost in this tank itself based on all of that. Okay, and I know everybody has questions on these points, so that's why I said you want questions. So lots of math that goes into that. Okay, and that really is our leak calculation process. Make sure we use all the data available to us, have a conservative estimate of what that data looks like, and then use all of the analysis that we have on the types of waste and the ability of the waste to hold that interstitial liquid and the porosity and the capillary heights of that waste. Okay. So then, so I mentioned this. So really the analysis here is how do we mitigate any subsurface contamination? And so you see on the right there, I'll go through the picture really quick. We do have a groundwater operating system, groundwater treatment system. It is in place and it's been operating for many years now. And it was to mitigate any contamination under B farm and B complex, really, from past operations. Old project that determined somewhere 52 million gallons of contaminated liquids were discharged into the soil and disposal sites in and around B complex, and about 360,000 gallons of contaminated liquids from past leaks from multiple tanks in B, BX, and BY farms. So this groundwater treatment system is a large network of subsurface piping. Takes it to a pump and treat system that then removes the contaminants so that it can be released. So in context of that, this treatment system is pumping around 6 million gallons a month, capturing and removing this contamination. And based, as I mentioned, in terms of risk versus margin, that margin of how much liquid is being removed and treated with leaks that then contribute to that, that's a large margin of the capacity of the groundwater treatment system in terms of what is additional contamination that may be due to this leak. So tank B109 leaked around 3,100 gallons, but as we continue to monitor that, it is defined, not defined, it is designated as an active leaker. So that number is likely to rise at some small pace as it is going, 3,100 gallons over 7 years. So we're interested in making sure that the groundwater treatment system continues to be effective and has that large margin versus how much water is being pumped through that treatment system to accommodate any of these changes as part of our tank integrity program. So at the estimate from some subsurface modeling is that 25 years, and that's not just related to this particular material, but the subsurface modeling around B109 and B complex shows it'll take somewhere around 25 years until it reaches the groundwater, and which is 210 to 240 feet below the tank. So obviously, from the lots of work done on subsurface and geographical modeling for subsurface transport and flow, not only for this particular case, but a lot of the work that we do in terms of handling subsurface contamination. Okay, next slide, please. So I wanted to go through this. So some other mitigation options and some challenges with those mitigation options. We're already expanding our groundwater treatment system by adding an extraction well. And then one of the things that are important to us is install any ventilation to evaporate liquids in the tank. It does require, obviously, and B tank farm requires some new infrastructure in terms of power and utilities, something that's under consideration. Ventilation is a good way to remove if there was evidence of water intrusion on the surface. It's a good way to remove water from the tank itself. So kind of two thought processes there. One way to prevent leaks is to remove the water by ventilation. So that's a process that we've used pretty effectively in some other tanks. Install surface barrier to divert precipitation. And we've done multiple surface barriers in multiple tank farms now. And that really is to prevent recharge from any rain that then would cause the contamination to be able to be transported faster with rain recharge. So those are effective techniques. Remove pumpable liquids again. Obviously, this would require new infrastructure. And this really tends to have a limited effectiveness. When we say the reason that interim stabilization used these particular terms in terms of pumpable liquids is that when we have pumpable liquids, it means that the liquid must be available and be able to move to the spot in which the pump is. And so we have limitations on pump technologies, as well as we are at the where how the tank chooses, how the tank behaves, and how the water moves to the one spot where the tank is, or I'm sorry, where the pump is the limiting factor. And that was a lot of work done in interim stabilization. In contrast, right? So as a contrast to that, in the ventilation system, we tend to run ventilation over the entire surface versus waiting for liquid to come to the one spot where the pump is. Retrieve and transfer waste, obviously, at some point in our future. This is part of the program, part of the plan. It will require a significant amount of infrastructure to do that. Probably everybody on this call knows how we do retrievals. Lots of power, lots of pumping, lots of places to take it to. So we've gotten good at that, but it will require pretty significant new infrastructure to be able to do that. And that is also under consideration. So, we've talked about the testbed initiative equipment. A couple of things to really remember about that. This tank is just looking at the design of the testbed equipment. This tank is, like I said, about 8 feet shorter than SY Tank Farm. So the physical equipment itself is a little long. In addition to that, the testbed equipment is filtration, followed by ion exchange for cesium. And this tank really doesn't have very much cesium in it. And in the way that CST, crystalline silicotitanate, works is that there is if you were to remove cesium, there is a molarity that's required for it to work at its highest decontamination factor. And that molarity is somewhere around 5.5 molar sodium. 5.6 molar is our spec, maybe a little more concentrated. So in order for us to use something that requires, or that would remove cesium, like an ion exchange medium, like crystalline silicotitanate, we would have to adjust the waste in this tank by adding water to the salt cake on top, going back to the pictures. And we'd have to add water, which is counterintuitive, to get it to the right molarity and the right chemistry for the cesium ion exchange to even be effective. CST, one of the good things about CST is that it does work in high pH situations and it's stable. However, it does require sodium molarity and some of the other things that will compete with cesium itself. We need to get that into the right chemistry space so that it removes the most cesium possible. So some physical limitations, some just chemistry limitations on what we would do in terms of ion exchange in this tank. And then being able to, obviously, we have to have some infrastructure to be able to do that and be able to dispose of the material that came out of it. So two things out of there. One, again, as I mentioned early on, it is important to note that this is a 500,000 gallon tank versus a 1 million gallon tank for which the TBI equipment was actually designed and fabricated. And then the second is we have to be able to adjust the chemistry in the tank for the cesium ion exchange to be effective. 5.6 molar sodium is the nominal concentration of chemistry that we like to get to. And then, certainly with the Department of Energy, balance options with any commitments that the TPA or consent decree or near-term tank waste retrievals and treatment of low activity waste may have. So all of these are options. We have considered a lot of these options. They all have pros and cons to them. Already underway in terms of groundwater treatment system, adding margin to the already 6 million gallon treatment capacity, ventilation to evaporate water in the tank. Will require some new infrastructure, but that one's could be a near-term solution. Surface barrier. We are continuing to install surface barriers. Certainly pumpable liquids. We have the technologies in terms of pumps, but then we're still limited by how the waste gets to the pump, and is it pumpable? So I just want us to remember, pumpable doesn't mean because it has a pump. It's because the pump is in the space in which the liquid is available. Retrieve and transfer waste, I think we all know that one. Some physical and some chemistry limitations in the near term, or physical for sure. Chemistry limitations and the idea that we have to add water to get it to the right point for anything like a testbed initiative, anything like ion exchange to be viable. And then all of the other commitments that need to be balanced in terms of regulatory commitments on the part of the Department of Energy. So, all right, and then lastly, I believe this is the last slide. So you know, I think it's from the standpoint of how B109 was monitored, but not only B109, it is all of our SSTs. We have a document 9937, and we take the requirements in that document seriously. And we have a technical, rigorous process that follows not only a formal leak assessment process, but we track every piece of data that obviously that we get. The entire engineering team, I would tell you, tracks every piece of data. They are careful. They're technically, any indication is thoroughly technically evaluated. We do know as we go through that, and you saw the choppy work of the ILLs, they can be caused by multiple conditions. We know that. In any case, any change in those ILLs is tracked all along the way. If there is a technical, as we see some significant changes and the waste doesn't restabilize, then we enter a very comprehensive formal leak assessment process to go through all of the data in this particular tank's history. And then that includes analysis of leak rates. The same technical process, this process was followed for B109 as we increased, and I think you saw that in the graph, while we monthly monitor and we do visual inspections, but then if we see any changes that we'd really like to get a better trend analysis on, we'll go into quarterly, we'll go into a monthly analysis. If it restabilizes, we'll use all that data, and our programs continue to evolve in that. So all of this technical interpretation is publicly available. I think this is the leak assessment report. I don't have the report number in front of me, but it's all publicly available. The DIL data, the drainable interstitial liquid data is also available in the monthly tank waste summary report. And then in addition to just the current groundwater treatment that's there really for the 50 million plus gallons, we are considering other mitigation options, specifically not only to B109, but that B complex area. And as I said, and then lastly, as I said, we have so much, our margin at 6 million gallons for groundwater treatment versus the change in the total subsurface and how that margin of processing capacity really doesn't change how that margin is in terms of mass or volume. And so continuing work along that, and being that it is far underneath the ground, certainly no immediate risk to this, like a surface spill might be. So, and I think that's all I had. And then lastly, I would just say all of these mitigation measures, we're continuously collaborating with our regulatory agencies to ensure, and the department, to ensure that all the technical pieces are always considered, pros, cons, and otherwise. And continuously evolve our program in tank integrity, tank monitoring, technology, not only for the SSTs, but for the DSTs. Okay, and I think that's it, Ruth, I believe. And then with that, we'll take some questions.
Right. I'm going to check in with Nina before we do that. Are you with us, Nina?
I'm here. You were a little echoey there, so I wanted to be sure that you were ready for me. Just for people who don't know me, I'm Nina Menard. I work with the Department of Ecology, and I am going to speak to some of what Karthik said in his presentation. He did an excellent job of presenting the RPP 9937 process, and it is a difficult thing to determine whether a tank is truly leaking or if there's other factors that come into play. Some of the other things I do want to mention, though, is as a regulatory agency, we are committed to abide by our regulations. And so allowing a tank to continue leaking and not having DOE address that leak is probably outside of us applying our regulations. We are still working with DOE to come to an agreed order on this issue of a leaking tank. Some of the things I'd like to address that was presented here as remediation or mitigating technologies that were being used. Ventilation was one of them. The only other time I know of that ventilation has been applied, and my knowledge is limited, is on another tank. And although ventilation does evaporate liquids, it is only good on evaporating the liquids at the top surfaces of the tank. It does not really get down to the liquids that could be entrained, could be free liquids that would reside on the bottom of the tank, and that's where the leaks usually are occurring. The surface barrier. Yeah, a surface barrier would help with preventing intrusion of snowmelt, rainwater into the tanks. It does not stop the leak outside the bottom of the tank. I do want to make you guys aware of that. As for the pump and treat, there is an active pump and treat that is occurring in the B complex. It has been occurring for a number of years. In fact, we are on the cusp of approving the interim record of decision for the 2 groundwater units that are under the B complex and the C and AX complexes. And that record of decision will allow an expansion of the remediation of the groundwater in the B complex. But I wanted to point out too that we have a gradient. They talk about a lot of liquid discharges from the various B complex tanks that have leaked in the past or have been spilled in the past. Those are farther down in the Vados zone than this current leak. And I was glad to see that there's an estimation of at least 25 years before the current leak would reach groundwater. But if we don't do something to stop that leak, it's going to continue to leak. And you know, we could potentially be having pump and treat going on for 50 years to address that leak at this point in time. And by the way, that number's just off the top of my head. It's just off the top of my head, but it's still valid that the pump and treat could continue for many, many more years if we continue to have discharges to the Vados zone from these tanks. I'm looking at my notes over here. I think Karthik's determination, DOE's determination that the TBI is not a viable option in this instance is absolutely correct. I've inquired of our ecology staff engineers, and they also have said that it's just not a viable technology in this instance for this type of situation. And looking over here, the other thing I wanted to point out too is we're really only beginning to come into problems with SSTs and them deteriorating more and more. Right now we have B109. We also have a concern with T111. I only anticipate that we will see more SSTs continue to deteriorate and continue to leak at various times, and coming up with a viable program to address those leaking tanks, I think is an essential thing for the regulators and DOE to work on. One of those things is the process for the RPP 9937 is a good process. It only identifies the leaks. At this point, what ecology would like to see is for DOE to work with us to develop a leak response plan. And that plan, in my view, I see as a plan to evaluate what the leak is, what's going on, what the tank is, and have a toolbox of different kinds of technologies that could address those potential leaks as we go forth into having a situation where deteriorating SSTs are going to start to leak. Retrievals, yeah, I think we're looking at retrievals going on for at least 40 more years. And so the condition of these SSTs will be questionable as time goes on. At that point, I think that's about all I have to say in response to DOE's presentation. And of course, I'm available for questions. Thank you.
Right. I have 4 people who've indicated they've got questions. I would anticipate that list will grow. Let's start with Jerry Paulette and then move to Steve Wigman. Jerry. Let's make sure you're off of mute so we can hear you.
Thank you. I'd like to ask if either we would put the slide back on showing the graph, or I could share the same slide showing the drop in liquid level.
Okay.
Should I
let me do one thing and I'll throw it up there. I want to make sure I get the cue right. So the graph.
I have it if we need.
This one. This is the one you're looking for?
Yes, thank you. So first question is, why are we showing the slide as of months ago? Isn't the current liquid level now down to about 39.3 inches, representing another significant loss that would be several hundred gallons as of the August 14th data point? Secondly, when we look at the decrease of 1.2 inches from December 2018 to February 2019, that represents a loss of 4 gallons a day. And I guess my question is to both Ecology and USDOE is, what does it take if you see something like this to not report a leak when the law requires immediate reporting of evidence of a release into the environment? Didn't this go below USDOE's own rather extremely generous lower validation line? And then I'd like, and the third question is, let's talk about the increase. We see here, and this is work that Dirk Dunning, who many of you are familiar with, has calculated with Heart of America Northwest, that the rate of increase is pretty steady for 15 years approximately. Then you have what appears, and some of the experts said appeared to be a leak, that a perforation that may have plugged, and then the level went back up, but the increased level ended. And that's because this waste is hygroscopic, right? Isn't it? It attracts liquid, as well as there's likely evidence of intrusion. And DOE in 2014 said that this is a tank that is likely experiencing intrusion as well. So the proper calculation for the lost liquid should be taking into account the monthly increase rate due to the hygroscopic nature, not just the loss from the top of that circle at basically, which was December 2018, to the level shown here, plus the level that's now lost, which is now down to below 39.5 inches, if I'm correct. So can you address, isn't that line indicative of the waste level attracting moisture and training moisture, and that the leak will continue to be fed by moisture? And my final question, which goes to Nina, and thank you for your points you made, Nina, is that doesn't the law require without no one else, a regulator or the energy department, isn't the policy already set in law and in stone that when a leak from a hazardous waste tank occurs, the waste must be emptied as soon as feasible? And that's not mitigated by, well, we already have contamination in the area. We're supposed to reduce the impact of leaks by removing waste. Isn't that true? Now let me ask that to start with and then go back to the implication of the liquid loss, liquid gain, and shouldn't we be calculating? That's why with Dirk Dunning, we estimate that the liquid lost from this tank is already 180% to 3 times greater than US DOE has reported. So let's start with, doesn't the law require emptying the pumpable liquid? And can't we do that with salt well pumping?
So I can answer for the regulations that we have. And the regulations do say that once a leak is confirmed, and that's what the process for the 9937 document is for, is to confirm that there is a leak, and that was confirmed in April. And we are negotiating with DOE to determine being able to stop the leak. It's not remove the waste, it's stopping the leak is the way the technical regulation states. To prevent waste from escaping into the environment as soon as practical. And we are working with DOE to come up with what that would be. And that's about all I can say at this point in time.
Doesn't the regulation specifically say waste will be removed immediately or as soon as possible? And I can give you the regulation and cite it.
I can look it up right here, but it says the leak has to be stopped as soon as possible.
Well, there may be multiple regulations, but it's pretty clear. The language.
WAC 173.303 is the one I go by. So anyhow, I could look that up right now, but I can send you that information. I have looked at that recently. At this point, I tried to write down your questions. Is there something else that?
Well, the implication of the leaking liquid being limited, isn't there significant implication by the increase in the trend line for that indicates that this waste will continue to attract liquid and feed the leak?
That hydroscopic thing, is that what you're specifically speaking of? I talked to our head chemist here, and that was a new one on him because he says, to the best of his knowledge, the waste is not hydroscopic. And so I'm not a good person to answer that. Maybe Karthik has a better answer for it, as he may be more familiar with the waste, but we had not heard of that concept before. And our head chemist has stated that he doesn't think the waste is hydroscopic.
Karthik, do you want to help here?
Yeah, sure. So the hygroscopic is a very general term for salt. So hygroscopic is the terms we want to be using is deliquescence, not hygroscopic. All right. Yes. And so salts, deliquescence is the independent variables of the humidity and the temperature and the mixed deliquescence, and that gives energy for whatever the salt is. Okay. Well-known phenomenon in our tanks. So lots of work has been done on this in terms of corrosion and the opportunity for salts to re-solution in the tank walls and so forth. So as an example, sodium nitrate, which is a primary contributor to our tanks, deliquescence at room temperature is somewhere around 75% humidity. And so if you were to use whatever we have in our airspace at 75% humidity, we'd have to have 75+% humidity to actually absorb any liquid from a relative humidity water standpoint that's non-condensed. And so we know that phenomenon. If you look at the pictures of this tank, it's not really, if that was the case and it was 75% humidity, you would see a salt pool or a liquid pool on top that was complete. And we do see that in some of our, as we see some seasonal variation on the liquid pool surface just by seasons alone by relative and ambient humidity. So it's not just nitrates. In contrast to that, hydroxides have a 6% relative humidity at room temperature for deliquescence, give or take. And so nitrates and nitrites are very high. And as you go through, and if you do cycle about this, it will immediately evaporate it again. So hygroscopic, like I said, is a very general term. It's the deliquescence point and the efflorescence point. So deliquescence, you absorb it. Efflorescence, you immediately let it go. So this is more indicative of these, you talked about that. So I had a second question too. So what we see here is remembering that we know the deliquescence and efflorescence points of these combined salts to be in that range. Waste movement in the tanks itself, and then rainwater intrusion. We haven't confirmed that through visual inspection like we have in others. And to your first question was, do we continue to track the ILL? We are continuing to track the ILL with the latest. We continuing the analysis. So I think 3 points to the 3 questions. One, waste is hygroscopic, but not in all conditions. All salts are dependent on their deliquescent and efflorescence point. So if you take a sodium nitrate or sodium hydroxide, the humidity is what matters, although they all may be hygroscopic. Typically at 75% deliquescence, you'd see a pool on top. Some of these changes are really waste movement, and are they pushing around the LOW, or is there gas bubbles that are moving the waste around? And then lastly, we continue to track the ILL. You asked a question about, do we have another data point? We'll do that analysis.
Right. We've got 5 folks who have
Hey,
questions.
Ruth?
Yes.
Ruth, this is Nina. I'd like to clarify Jerry's question a little bit on the regulations. Why Karthik was talking, I went and looked them up. And yeah, you are right. The DOE should remove the waste as soon as practical to stop the leak. So a little bit of fine reading, but I just wanted to verify that, yeah, you're right. It's remove enough waste to stop the leak.
Thank you. It's 303-640 sub 7. The earliest practical time, remove as much of the waste as necessary to prevent further release, right?
Yep.
And removal of the waste. Yep. Thank you.
Mm-hmm.
All right, Steve Wigman, you're not only next in queue, you're also the chair. I suggest we push the break back a smidge and respond to questions and comments, because we've got 5 people in line.
I think that's a great idea. This is a very important subject. My question is almost a comment. I really like the idea of the agencies working together on a long-term response plan. I think this tank, in my mind, is a red flag, that we're going to have a lot of red flags. If we don't start dealing with it, we're going to be having this argument about every single shell tank we've got out there before we finally close them. And I would urge that we figure out a way to begin the closure process and not just leave these things sit there until they all leak. So that's my 2 cents.
Jeff and then Pam. Jeff?
Thank you. I'd like to challenge a couple of things that I've heard, but I do have 2 questions I'd like to ask at the end. First, I'd like to read a sentence from the derivation of best basis inventory for tank B109. It says that a comparison of photos from 1985 and the video taken during an intrusion evaluation performed in February 2014, when you show that picture of the pool, confirmed the previously dry waste is now covered with liquid over a portion of the waste surface. To me, that seems like confirmation that liquid that wasn't there before came in over time. that seems like something maybe we could agree on. Now, what is the exact source? What is the exact rate over time is unclear. I would just like to challenge on that. There was another thing I heard you say, Karthik, about the molarity, the salt molarity of the liquid, the interstitial liquid, and whether it would be compatible with the CST resin that's used to strip out cesium. You said that it would be too salty, basically. Based on the best basis inventory, some consultation I've been doing behind the scenes, I might be wrong on this. This is not my profession per se, but calculated 4.91 molar sodium, which is less than the 5 molar sodium limit for CST. So please, if I'm wrong, please correct me. But what I've come to understand is that it would be compatible with CST to remove cesium and strontium. And the purpose of Testbed Initiative, to my mind, isn't about proving out that straw, that too long straw in the tank. It's about proving out the concept of, if you could get liquid out of a tank, are there other ways you could treat it that would allow you to dispose of it in new ways, such as off-site? And the purpose of the CST resin, you can put it in different containers. Tisker is one such container. This, in-tank pretreatment system straw is a different type of container, basically just to run liquid through this resin, which is really the magic stuff. And so the idea when we're talking about how testbed might be one of the Lego pieces to respond to future liquid removal efforts, the idea is really about, can we treat the waste enough to allow us to reclassify it as something other than high-level waste in a valid way to allow you to do something with it once you get it out. The last thing I'd like to challenge you on is this idea, this front end of the process. Can we even get the liquid out of these tanks? You talked about the very slow rate of waste trickling through the salt and the sludge to get to that point where you've sunk a well in a pump. Because that's what we did back in the 80s and the 90s, trying to dry out these tanks. And we reached a limit where we were just sucking very, very small amounts of liquid out, and it was determined that it just wasn't worth the bang for the buck anymore. Well, I would argue that the purpose is somewhat changed today if you're trying to respond to a leak versus if you're trying to do just kind of a general deliquification of your tank. But also, as I'll talk about in my presentation, there's this enhanced salt well pumping, which is basically make a wider screen. And they did it at Savannah River. They used 14-inch wide screens to get interstitial liquid out of their tanks. And what I hear, and please again, correct me if I'm wrong, that interstitial liquid contained most of the radioactivity. And so they were able to draw that out of their tanks first using this enhanced salt well pumping. So from my perspective, I see potential that maybe there's a way to get liquid out of a tank, and then once you get it out, maybe there's something you could do with it. And so I hope that we can hear some response there about feasibility of that. And that's part of why our advice is asking for a more formal assessment of options, because we want to get to ground on some of these things and see if there are different combinations of Lego pieces, if you will, that might give us a new tool. So now my questions. Nina kind of touched on this, but there's the focus on it takes 25 years to get to groundwater. I assume that's based on Tech 99, which moves the fastest, but I don't know. When would you turn the pumps off? Do we know? How has anyone done a calculation of how long we'd need to pump if we weren't able to stop this leak in its tracks? The second question I have relates to this idea that this is about more than just B109. Yes, B109 has somewhere in the neighborhood of 13,000 gallons right now, maybe less based on the rate, but just doing some simple adding up from the monthly tank waste status reports, the drainable interstitial liquids across all of the SSTs is 3.37 million gallons. And again, if I got my addition wrong, please correct me. Has anybody ever done a risk assessment to figure out what the risk burden cost would be if we failed to get to all those tanks before they released their interstitial liquid into the soil, and if we didn't have some way to respond? Basically, what is the cost of failure on that 3.37 million gallons? Has anybody looked at the risk in the past?
Would you like Karthik or Nina to start with that, or should we just leave it up to the two of them?
If anybody has answers to those two questions, I would love to hear.
So I guess I can answer the question on Tisker molarity. Okay, so I don't, it's not just the sodium molarity is one of the parts and pieces of our waste feed qualification program, but CST typically when you do ion exchange, it's interesting, 5.6 isn't the maximum molarity. It's interesting that the DS actually go down around 5.6. So as you get more and more dilute, it removes less because now you have other competing ions that compete. And as you get more and more concentrated, then the sodium competes. Right, so it's a complete analysis of that. So just like for Tisker, we do a complete analysis of sodium, potassium, all of the other competing cations that CST will compete with. And again, well known for that. So we haven't done the full waste feed program for 4.91 molar, but my presumption would be that we would have to add water to dissolve the salt to be able to do that, to get to that molarity. So I'm not sure if that's a solid molarity or a solutionized molarity, but that's a question that we can answer, right? We can look at that. In the enhanced salt well pumping at Savannah River, there's two parts. They did something many years ago called DDA, where they actually removed interstitial liquid for direct disposition. The newer ones that they're doing there is really to enhance their rate of salt blending to be able to feed their processes. And so we have ways, in this case, their waste is really all solutionized Purex salt cake or evaporator bottoms versus what would be in this tank, which is an old bismuth phosphate waste. So certainly as you, in those options that are being considered, Jeff, we'd go look at how do we improve our own salt well pumping. And you know, to be fair, I appreciate the idea. There was a different goal back then, remove as much as you can, as quickly as you can. So we'd have to tailor that if there's an opportunity to do that. I think those are my two questions.
Well, so my actual questions were, once you start your pumps 25 years from now, how long till you could turn them off? How long till you've addressed the risk? And then the other one was, has anybody looked at the cumulative risk if all of the interstitial liquid that's left in all the single shell tanks was able to leak before you could retrieve it?
So I will try and answer your groundwater pump and treat question. The groundwater pump and treat in the B complex is ongoing at this moment. The groundwater that is pumped out of that system is transported over to the 200 West area and treated through the water treatment facility that is currently there. And so that will be ongoing. The estimation that DOE gave of the waste that's currently being discharged to the environment from B109 would take about 25 years to actually hit this pump and treat. So you're looking at it probably continuing to operate for at least 25 years. Yeah. And who knows how long it would operate past that. Now, overall, if you look at the contamination in the 200 area central plateau for groundwater, some of the information about how long the estimation that the pump and treat would have to operate would probably be contained in the feasibility study for the 200 ZP1. And that's the feasibility study that created the record of decision that built the water treatment facility. At that point in time, I don't know if that record of decision included the possibility of waste from the east side being transported to that water treatment facility. It's been a long time since I have looked at that record of decision, and it's probably has been amended. I'm not familiar enough with it, quite frankly. So at this point in time, with a new contribution to the Vado zone that we have realized, the realization we could have other contributions to the Vado zone that either could happen in the future. That's kind of an unknown area there. But granted to say, it's going to at least go on for another 25 years and probably a good bit more beyond that. And then you're looking at also having to update and replace the water treatment facility because it's got a life cycle to it also. That's another realization. So I can't answer you the question about when can we turn the pumps off. So I hope that's provided you some information on that area. Did I answer your questions, Jeff, or do you have some other questions?
Well, you answered that one as well as I would have expected, so thank you.
And really, when it comes to the more technical part and the salt well pumping and things like that, Karthik is much more the expert than I am.
Right. I have Pam, Richard, Chris, and Liz in queue. Mike Karenko, you can test your *6. I'm trying to keep the background noise down, so that's why I've been muting people to try to help keep that down. Pam, you're up.
Thank you. I have a question and then some comments. So the statement that 52 million gallons was discharged in the vicinity of B109, is that from cascading?
I'll answer that. It's not just from cascading. Actually, it's of discharges from reverse wells, from cribs and trenches. So it's not just from cascading. It's the entire operations that took place back then.
Okay, so
just to be clear, sorry, Pam, between the leaks from cascading and then all of the operations that took place by intention in those timeframes.
Okay. So I have a little different perspective on all of this. I mean, from sitting in on some of the tank integrity sessions years ago, this is just an indicator of tanks that are leaking because it's documented. Everybody is aware there's a bunch more. And so here's the question. From a financial perspective, do we want to take all our money, take it away from tank waste treatment, and go after some leaks? And in the scheme of things, with the pump and treat going on, this is not causing me to lose sleep. I do think a general comment was made that ecology needs to come up with a plan so that we can close tanks. And I really like the concept of the toolbox. So in terms of resource allocation, let's look at across the board. This tank is an indicator, but we're going to have more. And so from a budgetary and scientific perspective, what could we build in the toolbox to address these things as we go forward? But our pump and treat system is pretty spectacular. And my priority is tank waste treatment. And we're darn lucky to get the allocations we're getting from Congress. Really lucky. And it looks like we're going to be good this year. The House is generally a little bit higher than the Senate, and we don't have the Senate numbers yet. But I mean, who knows what's going to happen in future years? And we need to look at this from a resource management perspective. Thank you very much for your presentations.
Right, Richard, I see your hand and you're next.
Okay, and I come up and ask, I got two questions. One is, we were asking a question when the pump and treat would end. My question is, when did it start? Does it correlate in any way with these drops? And
no.
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 Well,
So the pump and treat's been going a good probably almost 10 years, and DOE may have more information on that than I do. But the B complex pumping started about, I want to say 6-7 years ago, and Karthik may have more information on that than I do. That's the best of my memory. But originally the treatment the water treatment facility was addressing groundwater contamination in the west area, and then the B complex was added. And then as we implement the new record of decision that should be signed this week, hopefully, keep your fingers crossed, we will then be adding treatment from around the C farm and the A and AX farm also into that system.
So you've just confirmed what I said. It does correlate. They started B plant pumping at about the point that this curve started curving down. Second question is, technically, I know we have mixed sampling information on tanks, but do we, I mean, not 1 gallon of liquid is equal to another gallon of liquid without considering what the content of that liquid is. The interstitial liquid, how does it compare radiologically to the actual salt itself? Because obviously the sludge, you know, from my work on AY102, the sludge had a significantly higher radiological concentration than the salts. Salts were more of an insulating issue for the sludge that was on the bottom of AY102. And as I remember, my memory doesn't serve me extremely well, but the salts were mostly strontium. Is that correct? And what would the interstitial liquid compare to the other constituents, the salt or the sludge that's in this tank? That's my two questions of really what is it that we're leaking radiologically, not volume-wise.
I think Karthik's going to have to answer that one.
Okay, so salt cake is primarily so it's not strontium in the salt cake. So the sludge has all the insoluble solids. The salt cake is really for this particular tank, it's primarily chemical in nature with some soluble elements in it. And the interstitial liquid is whatever the interstitial liquid is in total concentration within the holes of the salt cake will dissolve whatever is in the salt, provided there's enough liquid in the porosity. So typically much more dilute than in radionuclides and much higher in chemistry than the sludge would be.
You're still on mute, Richard.
Okay, and I guess my follow-up question would be, so in this tank, I'm not familiar with that chemistry that produced this waste, but in this tank, would it be considered a high heat tank or high activity tank compared to some of the other ones? No.
This is a much older style tank that had some cladding waste and some other things, in contrast to a Purex type tanks, which is a very efficient process. Again,
So,
older process, right? So very high in chemicals and so forth.
So in preparing the notifications for leakage, is there an estimation of Curie leakage?
Not that I'm aware of.
All right, thank you.
Right. I have Chris and then Liz. Chris?
Yes, I have two questions regarding the 25 years to reach groundwater. Generally, modeling such as used to generate that 25 can yield a range of results depending upon the sensitivity of the model to various input parameters. So that 25 is really 25 plus or minus something depending on the sensitivity of the model. I'm wondering what that plus or minus might be. So that's my first question. The second question is, what does the 25 years refer to? Is it just the liquid part of the leak? How long does it take the water to reach the groundwater? Or is that how long it's going to take the cesium in it to reach the groundwater? Or what is that 25 referring to now? Because different constituents in the leak will have different absorption coefficients that will dictate how fast they really move through the vadose zone. So
Karthik, I'm going to point to you.
Okay. So I think we're going to have to go look at the details of the modeling. And 25 years, as you were correct, has a sensitivity. I'm not aware of the exact sensitivity analysis that was done. We can certainly get that information to you. And the exact nature, and I think Jeff also asked the question, the nature of which contaminant did they track?
Yeah, because if the sensitivity is 25 years plus or minus 25, it can make a real difference if it takes 50 years to reach groundwater than if it takes a year. So
yeah, absolutely.
That's why I asked the question.
Yeah, we'll go look at the details of the report and tell you what the sensitivity analysis was. Just in general, I would say that because of the known contamination, certainly in B complex and T complex, there's been a long history of this modeling. So I want to make sure you get the correct data particular to this model.
Okay, thank you.
Yeah.
So that means we've got Liz and then Mike Karinko. Liz.
Hello. Thanks for this conversation and for being here to talk with us, Karthik and Nina. I'm wondering, I saw about the ventilation as a way to evaporate liquids, but has any work been done, and this is not my expertise at all, but I'm thinking more about, is there a way to include some kind of route, like an evaporator in all of the SSTs, something that could just be part of routine maintenance, so that it's not, we're not working in like crisis mode, or oh, now there's this thing we need to deal with, and do we go get that, or do we deal with all these other things we need to deal with? It's just built into a situation we know that's going to continue to be problematic. And I think that the idea of using pump and treat to address all future tank leaks is problematic to me. So I'm just wondering if there's a way to deal with just evaporating liquids in these tanks, or if that's been looked at. And I don't know how ventilation works. Maybe that's something for a future tank waste committee meeting to really understand what those options are. Just to make this not be an either or situation that's just relying on the waste leaking and then getting it later out of the groundwater. It just seems like a really challenging situation. And I'll also just point out for Rob, if you put your question in the chat, and Ruth also wrote to you, I'm happy to ask the question for you. But since Rob's a lapsed member, he has to wait for the public comment time. Anyway, any thoughts on that? And maybe it's like a totally silly idea, but I'm just curious.
So I can take the question on the how ventilation works and evaporation. So typically the way we have active evaporation is we will have a liquid surface. So Ruth, if you could go to the surface pictures.
Yeah.
And I don't remember which slide. Oh, there it is. Okay. So in a tank that has a significant amount of supernatant on top with a liquid portion, typical of a double shell tank farm, you'll have a lot of liquid on top. The way evaporation works is that'll be at a particular specific gravity. We will take that liquid, send it to an evaporator via transfer, and then send back a much higher concentration solution with a lot less water. So that's an active evaporation. So active evaporation in this, we'd have to dissolve the salt and then send it back, which means adding water to get rid of the same water we added. That's one piece. The second piece is in ventilation. What that means is that we would run air over the surface of the existing liquid and remove the water. And I think, as Nina might have mentioned, it's very effective at removing water on the surface parts. But as you go through that process, it reaches some equilibrium condition. And we talked about deliquescence and efflorescence and dry. It will reach some equilibrium, and it will pull water at some slower rate than just water on the surface. And we saw that in the one other tank that we had, as she mentioned, had exhauster on. That it worked very fast at an early rate, and then it slowed down to a plateau equilibrium condition, pulling out water that has to transport to the top to get there. So very different in active evaporation versus ventilation running over the surface of the tank.
And is it some? I'm thinking, because I have a dehumidifier that pulls water from the air. Like, there isn't a way to have, like, if there's a way to pull the water into a place that you can then pump it from, you don't have the same issue of needing the water to be draining into the place where your pump is. And I'm sure that's also looked at, but
yeah, that would be an active ventilation where you're evaporating water and leave the surface dry, and then also addressing, as Jeff mentioned earlier on, even though we haven't seen physical evidence of rainwater intrusion, right? It's on the list of, not physical, visual with a camera. We have seen liquid pools on top over that 30 years that it was in there when we went back in.
So with active ventilation, there's a couple other things to consider as you talk about that. With active ventilation, as you are evaporating water, you are also evaporating a lot of other contaminants. So you would have to have some sort of treatment of the air that goes off of the tank before it can be discharged into the atmosphere. So that's something that kind of complicates doing ventilation also. And something to be aware of, that it probably would not be feasible to put it into every single shell tank. The other thing too is, as you dry this waste out, you could come into problems in the future with being able to retrieve that waste, because it could become as hard as the ground or as a rock, or there could be other issues with being able to retrieve a dry waste at this point in time. Over.
Thank you so much.
Right. Mike Karenko, did we get you off of mute?
I don't know. Can you hear me?
Yes.
All right. I'm bursting into a song here just to take opportunity here. Two comments. If I'm listening, I really like the idea of developing toolbox to deal with the situation. But what I was a little surprised about is that this same toolbox is the one we should have already developed if we're going to be really serious about emptying the tanks for the VIT plant. So there's a similar set of toolboxes, and we better combine the functional requirements. So as the point was just made, we don't shoot ourselves in the foot for ultimate retrieval. But I sit back and I think, do I know a list of tools? How are we ultimately going to get rid of the waste in a single cell tank for the high level vitrification? I'm not sure we've really thought this through in a disciplined way with here's a concrete set of tools that we've been developing in the time that we have left before we built the high level glass plant. That's just a conceptual thought. Another one, this is probably heresy, is on the pump and treat. I mean, water is evil. We're going to be putting caps on it. And I'm going to take a contrarian view, is that I've always been concerned that we put the stuff in a Vadosphone and it's going to stay there forever. Why don't we consider another option, for example, as a brainstorm, columns of water to flush that stuff out to the active pump and treat system? Why are we afraid of water? It's going to come to a diminishing return until some future rainstorm that we're long gone with. So ultimately, conceptually, I still think we ought to examine the Vado zone and the ultimate solution. And the pump and treat is a great success. It makes us comfortable in the near term of our lifetime. But ultimately, we better figure out how to clean up that Vado zone. And I'm betting that water flushing is a tool that we might engage. Not now, because we got other priorities, but there's some conceptual thinking for my grandkids, I think. But just wanted to make those two comments. Thank you. And I won't sing a song.
And you won't sing a song?
No,
Okay.
I sing in the shower and the water turns off.
More water. Steve Wickman, you're next. I'm going to propose, before you jump in, that we entertain your questions and comments and Jerry's, and then open it up to public comment on this topic in case we have either lapsed HAB members or members of the public who wish to share a comment on this as well, because we're in this awkward space. So, Steve, take it away. Are you there?
You mean me or Steve Anderson?
Oh, I mean Steve Wigman. Good
Well,
catch.
Up and then I put it down. I was kind of curious about, as I try to mentally evaluate this situation, I go back to when we interim stabilized these tanks, and we did seal them quite a bit, didn't we, as far as intrusion of water? It seemed to me we cut the pipes and capped them and gun-eyed all the access points. Maybe that's not relevant anymore. That's just, we did a lot. We did everything we could at the time. And I'm wondering, is there an interim stabilization phase 2 that we can incorporate into our thinking?
Are you musing or do you want an answer?
Well, I guess let's move on.
Okay. I didn't mean to cut you off. I just didn't know.
No, you're right. I think, we're down in the weeds and we're a policy organization, but, it's an important set of weeds to wall around it so you can understand the policy. So I'll just let others talk.
Okay. Jerry, you're next. And then I do want to open it up for public comment to help more voices at least be heard. So Jerry?
Yeah. So we've heard a bunch of excuses for not doing what the law requires today. One being, we got pump and treat already. The Tank Waste Committee has seen the gamma borehole logging, which is literally off the charts between about 50 to 60 feet below level of the top of the tank and below the bottom of the tank. Groundwater is 200 feet, and that's just the gamma. And so one question is, why the hell aren't we doing additional borehole monitoring around the tank so we know what the radionuclides are and not just the raw gamma and how fast it's migrating? Number two, the excuse that, oh my gosh, it's going to be expensive to use enhanced salt well pumping. Didn't US DOE do a report on responses for tank leaks and had its own people? It chose who was involved, did its own ranking. Again, Tank Waste Committee members, I believe, have seen this, and Jeff's presented results of it. But didn't you do your own ranking that basically said enhanced salt well pumping is as good as ventilation? But what you didn't consider is what Nina said, is that with ventilation, you've got an air emission problem. You didn't have a single person with industrial hygiene and vapor prevention and health issue considerations on your panel to do that. And without it, ventilation actually ranked much lower, and the air permit had to be pulled for T111. So And the third is the cost of deploying. And I'd like to hear, what is the cost, since salt well pumping was rated as being available, very highly available technology, and you can use a mobile tote. You don't have to put in all the darned infrastructure and costs. You can use the mobile tote for removal of the liquid. What is the cost that we're decrying as being too expensive to remove pumpable liquids from a tank and have that equipment available, and then move it to the next tank that's at risk of leaking or is leaking, and to control the leak and remove leakable liquids as required by law? So what's that cost that you're saying is too darned expensive? Have you costed it, and where is it?
Does someone from DOE have an estimate of those costs?
If you don't have that, if you're looking at our advice and we're saying let's do an assessment of the options for B109, that needs to be part of the discussion, including whether or not you simply remove the liquid. I mean, the irony I want to point out to everyone is that you said there's too little cesium to do cesium ion exchange. Well, that's good news. Then just remove the liquid, as Jeff said, and you put in the removable tote and move it and test it for offsite treatment, or just, put it in double shell tank. So what is the cost option for whether or not you just use a mobile enhanced salt well pumping, whether or not you do TBI? What's the cost? And is that going to be part of the formal assessment? Are you even agreeing to do an assessment of these options?
So this Carly, I'll address the cesium question in the context of, I always react to the adjectives, right? So cesium concentration for the purposes of safe transportation are different than cesium concentrations for the purposes of ion exchange. And that we need to make sure that we understand what those things are. And so we certainly have not done the analysis yet of seeing if the cesium concentration, if we remove the liquid, would actually meet the safety standards for transporting interstitial liquid above surface in a mobile tote.
For that clarification.
Ruth, this is Stan.
Dan,
I just want
yes.
to add that Mr. Vance covered this morning that we're working with the tri-party agencies to address B109. So I think he pretty much addressed that this morning in his discussion. Thank you.
What I'd like to do at this point is open a little bit of time for those who we have to consider as members of the public who are HAB members whose appointments have lapsed. I see that we do have some comments from them. That also includes any members of the public who aren't lapsed HAB members who wish to make comment on this issue at this time. We're trying to help people be heard in an unusual set of circumstances. Bob, I want to start with you, and then I want to check in with Rob Davis.
Yep.
And we will go from there. Bob, Yama.
Yes, since I can only make a statement and not ask a question, I wanted to first thank Kartik for the excellent leak discussion. When the Tank Waste Committee started looking at the B109 leak, we asked DOE for some technical information. And we were told at that time that it was going to take a while for the presentation to be put together and approved. And since this was really time-sensitive advice that we wanted to give, we had to rely on our own committee resources to really look at all the technical and the issues in that chart that Kartik showed us. So my comment is we really need, as the HAB and DOE, to find a way where committees, the technical committees, can ask questions and get real-time responses on some of these points. And Kartik's presentation answered a lot of the questions that we brought up. And if we could have had that input during the advice development, it would have helped a lot. So that's my input. Thank you.
Rob Davis, I want to check with you to see if you've got a comment. Our conundrum is we actually can't respond to questions that come up during public comment.
Right. I understand that, and I'll try to think a way of just making statements. First of all, I'll just remind everybody the WTP should be working by now, and we wouldn't have this problem. So fully fund the pre-treat and HLW.